Alright, so I'm going to go through paper 2. So what I'm going to do is I'm going to go through all of the answers to the questions and kind of give you like an overview of how the marks are broken down. So I'm going to talk about things that would have been accepted, and I'm also going to talk about a few things that would not have been accepted. Now, of course, every individual will be a little bit different, and it really just depends on some of the wording that you might have used as to whether you would have gotten the mark or not. But let's go through question 1 for this video, and then what I will do is I will divide this into 4 videos, so each question will have its own video. So let's look at question 1. Alright, so we have phosphine, and it does tell you what phosphine is. Phosphine is a molecule of pH 3. It's asking you to draw a Lewis dot structure. So essentially, what you're going to do is you need to make sure that you have the appropriate number of electrons shown in your structure. So phosphorus, if you look it up on the periodic table, has 5 valence electrons. Hydrogen has only 1, and there are 3 of those. So overall, we should have a total of 8 electrons being shown. So phosphorus will go in the center. Hydrogen will never ever go in the center. Put your hydrogens around. Connect your outside atoms to your central. Well, I've got 2 leftover electrons. The leftover electrons go onto the central atom. So leftovers will go on the central atom. Extra electrons, or leftover and extra electrons will go on the central atom. If you run out, that's when you make double and triple bonds. Okay, so the next question. So you would have gotten a mark for this, and they would have also accepted if you just drawn a line. I just don't, it's not very proper, so just draw out your individual electrons. Alright, so outline whether you expect the bonds in phosphine to be polar or nonpolar. You have to remember for paper 2, you're going to get your data book. In the data book, you've got the electronegativity values listed in one of the first couple of pages. So if you go and you look up the electronegativity of phosphorus, that's going to be 2.1. If you look it up for hydrogen, that is also 2.1. This is one of the very few bonds that ends up being nonpolar. So remember, in order for a bond to be considered polar, you have to have an electronegativity difference greater than 0.4. So 2.1 minus 2.1 will give me a difference of 0. So technically, the bond itself is nonpolar because the difference in electronegativity isn't, well, it's 0. But if it's not great enough, then you're not going to have those electrons being pulled more to one side of the bond. All right, explain why phosphine is not planar. So remember, look at everything that you're answering. This one has 2 marks, so in order for you to get both marks, you have to say something about the fact that you've got a lone pair. So you've got a lone pair, okay, and you also have 3 bonding pairs. So you've got a lone pair, you've got 3 bonding pairs, but that's not the whole reason. It needs 2 marks. So you need to make sure that you also state that the lone pair repels more strongly. So essentially what you have to remember is that having a lone pair changes that bond angle. So when you have a lone pair, it's going to push the atoms closer together than they would normally be. So if it was just 4 bonding pairs, it would be a tetrahedral shape, and it would not be a polar molecule. This molecule, even though you've got nonpolar bonds, it does end up being slightly polar because of that lone pair. Alright, so phosphine has a much greater molar mass than ammonia. Explain why phosphine has a significantly lower boiling point than ammonia. Well, what is ammonia? Ammonia is NH3. So NH3 and phosphine have the same structure. Okay, the difference is nitrogen and hydrogen bonding together results in hydrogen bonding. So you have to have, it's 2 marks again, so you have to say something about the fact that there's H bonding or hydrogen bonding in the ammonia. Okay, and then the second mark comes from you saying that, which makes it stronger. So this would be stronger. So it's harder for the ammonia molecules to be pulled apart. So you have to talk about both of those things. You have to mention the hydrogen bonding, and then you also have to talk about how it's stronger. All right, so phosphine is usually prepared by heating white phosphorus, which is P4, one of the allotropes of phosphorus, with concentrated aqueous sodium hydroxide. The equation is listed right here. Okay, identify one other element that has allotropes. Essentially, this is a vocab question. Do you know what an allotrope is? An allotrope is going to be where you have the same chemical composition, but the structure is different. So one of the main allotropes that we do talk about is carbon, or an element that can make allotropes, rather. And one of the forms would be a diamond. Okay, and it could also be graphite. So we discussed both of these allotropes. Now, other possible answers, well, you could have said graphene. You could have said fullerene, which I don't think anybody really would have stated. Didn't really talk about it that much, but both of those are acceptable answers. All right, the next question. The first reagent is written as P4, not 4P. What's the difference? Well, remember when we have that subscript there, that indicates that you've got 4 atoms bonding together. So P4 is a molecule. And if you were actually writing this out, I would advise you write molecule instead of the shorthand NC of 4 atoms. Now, if you wrote it as 4P, is just 4 atoms, not bonding together. So in order to get the mark, you have to discuss both of those things. So essentially it's asking you, do you understand what a coefficient is, and do you understand what a subscript is? All right, so the ion H2PO2- is amphiprotic. Outline what is meant by amphiprotic and give the formulas of both species if it's converted when it behaves in this manner. Okay, and I was careful not to really elaborate what that meant, because again, this is a vocab question. You need to know what amphiprotic means, and then you also have to be able to do something with that. So amphiprotic means that it can behave as a Bronsted-Lowry acid and a Bronsted-Lowry base. So under the Bronsted-Lowry definition of an acid, and acids give up H's. Okay, bases accept. Okay, so amphiprotic means that it can do both. Okay, so you have to be able to explain what amphiprotic means, and then you also have to give, okay, so of this, what would it be? Give the acid version and then give the base. So what would it look like if H2PO2- gained an H+? Well, it'd have H3, so it'd have 3 hydrogens, and then the charge would go down to 0. Because you remember, you're adding an H+, not just an H. So now, what would it look like if you did the opposite, if you took off an H+? So if you took off an H+, you would have H, so just one H, PO2, and then my charge would go down to -2 because you're taking off an H+. Okay, so now the next question is asking about the oxidation state. So for P4, well, it's in its standard state, so the oxidation state should just be 0. So now you want to know what P is and H2PO2 minus. Well, oxygen will be a -2, okay? Hydrogen will be a +1. Well, everything needs to add up to -1. So -2 times 2 would be -4, and +1 times the 2 would be a +2. So +2 plus a -4 plus some number, which is what phosphorus would be equal to -1. Well, +2, -2, that would give me a -2 plus X. So that means that phosphorus has to be +1. Okay, and then also when you're writing oxidation states, make sure you write that positive sign first, because if you write the number after, like if you write the charge after the number, like we do here, that is indicating a charge. Okay, so if it's asking for an oxidation state, make sure you put the sign and then the number. They're a little picky about that. All right, so oxidation is now defined in terms of the change in oxidation number. Explore how earlier definitions of oxidation and reduction may have led to conflicting answers for the conversion of P4 to H2PO2 minus. Okay, and then now explain the use of the oxidation numbers, or how that's helped with that. Okay, so essentially what you have to know is you have to know what the old school definition of oxidation and reduction is. So old school definition of oxidation is where you gain oxygen. So it's talking about some molecule where it's gained oxygen. And you know, we do see this a lot with oxidation happening. Sometimes you'll see a molecule and it gains oxygen. Now, reduction, when we talk about that, that's actually defined as hydrogen being gained. Okay, and then that was an observation that happens all the time. Not all the time, but it happens sometimes. So it doesn't always happen though. Now, if you look at this molecule right here, P4 to H2PO2, well, it's gained hydrogen, it's also gained oxygen. So it has not been both reduced and oxidized. It's gone from a 0 to a +1. Okay, it has been oxidized. And then now what we do is we look at the change in oxidation state or number. So now oxidation number, or oxidation, which is the loss of electrons, but we can look at the oxidation number. If the oxidation number increases, then it's been oxidized. If the oxidation number decreases, then it's been reduced. So using the old school definition, you can't really tell what's happening to the phosphorus here. Okay, so the next question is math. 2.478 grams of white phosphorus was used to make phosphine according to the equation. Calculate the amount in moles of white phosphorus. Should be easy. You're just converting. So it's 2.478 grams of P4, and then convert that to moles. Okay, so when you're doing these questions, here's what I'm going to advise you. Because normally when we do this math and we're looking at the molar mass of the P4, you could say, well, it's 30.97. Okay, so you could say, oh, that's close to 31. If you want to be really accurate and sure about your significant figures here, just go ahead and actually use the whole number on the periodic table. I know it's a little annoying, but it helps to ensure that you're going to get whatever answer they plugged in. So it's 123.88. So if you plug in that number, that's going to give you 0.02, and then go to 4 significant figures here, and then that would give you exactly what they had. So whenever we're calculating out a molar mass, just go ahead and use the full number for paper 2 and paper 3. It's going to make your life a lot easier with significant figures. All right, right, so the phosphorus was reacted with 100 cubic centimeters of 5 moles per liter aqueous sodium hydroxide. Okay, deduce showing your work which was the limiting reagent. All right, so I know from the previous problem that I have 0.0200 moles of P4. Okay, I know that from the previous problem. Now, I was also told that I have 0.1 liters. So you can use liters and milliliters here. Just make sure that you can look at their problems and know that, okay, if I have a cubic centimeter, that's a milliliter. If I have a dm cubed, that's a liter. And remember, if it's to the negative power, it's per. It's under a fraction bar. So I have 0.1 liters. I'm going to multiply that by 5 moles per liter. Okay, so it's asking which is the limiting reagent. So let's just pick a product and go to it. So I'm going to go ahead and go to phosphine because if I look down here, it's talking about phosphine. So let's go ahead and just look at going to moles of pH3. So moles of P4 on the bottom, moles on top of moles. Look at your coefficients here. That's going to be a 1-to-1 ratio. So this will still be 0.02 moles of phosphine. So now do your second calculation, and you have to do some sort of math here, or you have to do some sort of justification in order to get the answer. So now we're going to do the same thing here. We're going to go to moles of phosphine. Remember, that's just the sodium hydroxide. So moles on top of moles, there's 1 phosphine for every 3 moles of that. So when I solve for that, I'm going to get 0.166 moles of phosphine. Okay, so now which one is the limiting reagent? Well, which one limits how much product we can actually make? That would be P4. So P4 should be my limiting reagent. Now, had you actually gone to grams or had you gone to any of the other products, that would have been fine. But I just think you can just do a little less work if you need to. So you could have, if you did say P4 and you had an acceptable calculation, so if you had gone to grams, if you had gone to a different product, it would not matter, you'd still get the mark. All right, so determine the excess amount in moles of the other reagent. Well, the excess reagent is going to be your hydroxide. So it wants to know how much hydroxide is left over. So you can do this 2 different ways. You can start with the limiting reagent, or you can just go ahead and start with your answer. So you can start with your amount of product and say, okay, how much hydroxide did it take to make the amount of product that I could make? Or you could start with your limiting reagent and you can say, okay, well, this is how much P4 is going to get used. How much hydroxide will react with this? So either way, you're going to get to the correct answer. So let's go ahead and start with the product. That's just always been my method. So now let's calculate, okay, how many moles of hydroxide did it take to create this much product? So go backwards to your moles of hydroxide. All right, so that's going to be 0.06. So remember, this is not your answer. This is how much was used. And it would still be true if you had started with your limiting reagent. That is how much is used during this chemical reaction. The amount that's left over will be how much did you start off with minus this amount. So we started off with 0.5 moles. You have to take the molarity and multiply it by the volume. You're going to get 0.5 moles, so that's what we started with. And then we're going to subtract the amount of moles used. And that's going to give you 0.440 moles left. Determine the volume of phosphine measured in cubic centimeters at standard temperature and pressure that was produced. Okay, so if you look at this, it's talking about standard temperature and pressure. It's talking about a volume. You could easily go to PV equals nRT and use that if you wanted, because you know that the standard temperature is going to be 0 degrees Celsius, and then you also have the standard pressure. However, if you remember, 1 mole at STP is equal to 22.7 liters. So really it's just a conversion because it's telling you it's at STP. Now the thing is, it's not going to be 22.7 liters because you don't have a whole mole. So how many moles do you have of phosphine? Well, we have 0.02, which we calculated up here. So again, like follow-through points still apply. So let's say that you got the incorrect number up here, but then you went down here and did the calculation correct, you would still get the answer, or get the mark. So this is how many moles I have of the phosphine. Well, how many liters is that? Well, I know that 1 mole is equal to 22.7 dm cubed, or you could just say liters. But it's not asking for it in liters, it's asking for it in cubic centimeters. Pay attention to your units. So, cubic centimeter over decimeter cubed. Well, 1 liter is equal to 1,000 milliliters. So you're going to get 454 cubic centimeters. So make sure you're paying attention to your units here.